There are transmissions that explain things. Signals that confirm what scientists already suspect. And then there are transmissions that don't fit anywhere. Signals that raise more questions than answers. Far beyond the outer planets, deeper than any human-made object has ever traveled, Voyager 2 continues its silent journey through interstellar space. For more than 4 decades, it has been sending faint whispers back to Earth, carrying data from a region no spacecraft was ever truly designed to explore for this long. Recently, something unusual appeared within those signals. What arrived through the deep space network was not just routine telemetry. Hidden within the weak radio stream were patterns, subtle, structured, and repeating in a way that didn't match anything typically expected from space environments. At first, it looked like noise. Then it appeared again. And again. These patterns were faint, almost buried beneath the background signal, but they showed rhythm. Not random interference, not simple distortion, but something layered. Something that made engineers pause and take a closer look. The timing made it even stranger. This signal emerged after a period when contact with Voyager 2 had already faced serious challenges. Over the years, its systems have aged far beyond their original limits. Power has been reduced, instruments have been shut down, and communication has become more fragile with distance. And yet, despite all of that, the signal carried a level of consistency that didn't quite match expectations. To understand why this matters, you have to go back to the beginning. Voyager 2 was launched in 1977 during a rare planetary alignment that allowed it to travel from one giant planet to another using gravity assists. This alignment, discovered by Gary Flandreau, made it possible for a single mission to explore Jupiter, Saturn, Uranus, and Neptune in one extended journey. That opportunity only comes once in about 176 years. The spacecraft went on to achieve something no mission had done before. It visited all 4 outer planets, capturing images and data that transformed our understanding of the solar system. It revealed volcanic activity on Io, detailed the complexity of Saturn's rings, discovered new moons around Uranus, and became the only spacecraft to ever fly past Neptune. Eventually, its mission shifted. After completing its planetary encounters, Voyager 2 continued outward, crossing the boundary where the influence of the Sun begins to fade. This region, known as the heliopause, marks the edge of the heliosphere and the beginning of interstellar space. Scientists expected this boundary to be gradual, a smooth transition between solar and interstellar environments. But what Voyager 2 detected was far more complex. The region showed turbulence, sudden changes in particle density, and unexpected behavior in magnetic fields. Instead of a calm boundary, it behaved more like a dynamic and shifting frontier. Since entering interstellar space, Voyager 2 has been measuring plasma waves, cosmic rays, and magnetic fields unlike anything observed closer to Earth. Most of these readings have been difficult but explainable within the limits of physics. But not all of them. Over time, certain anomalies began to stand out. Subtle variations in plasma oscillations. Repeating frequencies that didn't behave entirely like random turbulence. Small irregularities that were easy to dismiss individually, but harder to ignore when viewed together. The recent transmission brought those anomalies back into focus. Embedded within the data were repeating intervals that seemed too precise to be purely accidental. Some sequences appeared to align with the spacecraft's own transmission cycles, almost as if the signal environment itself was interacting with the probe's output. Scientists are cautious about jumping to conclusions. There are many possible explanations. Interstellar plasma can behave in ways that are still not fully understood. Magnetic field interactions can produce wave patterns that appear structured under certain conditions. Even aging hardware can introduce unexpected artifacts into transmitted data. But the combination of timing, repetition, and structure has made this particular signal difficult to categorize. Another factor complicates things further. As Voyager 2 travels deeper into space, the signal it sends becomes weaker and more prone to interference. The distance is so vast that it takes many hours for a single transmission to reach Earth. Detecting patterns within such faint signals requires extreme precision and careful filtering. Which raises an important question. If these patterns are real, where are they coming from? Some researchers believe the answer lies entirely in natural processes we don't yet fully understand. Others suggest that the interaction between Voyager's signal and the interstellar medium could be producing feedback effects that appear more organized than they truly are. At this point, no confirmed conclusion has been reached. What makes Voyager 2 unique is not just how far it has traveled, but what it represents. It is a messenger from Earth, carrying instruments built in another era, still functioning against all odds in a region that was once purely theoretical. Every signal it sends is valuable. Every anomaly it records is a reminder of how much we still don't know. The latest transmission doesn't rewrite science overnight. It doesn't confirm extraordinary claims. But it does highlight something just as important: the universe is more complex than our models, and even our best instruments can still surprise us. Somewhere in the vast darkness between stars, Voyager 2 continues forward, sending back faint signals that push the limits of human understanding. And for now, the mystery remains. As engineers continued to analyze the signal, they began comparing it with older recordings stored from previous years. At first, nothing unusual stood out. The same background noise, the same expected fluctuations, the same gradual decline in signal strength caused by distance. But when they isolated specific frequency bands and aligned them across multiple time periods, a pattern began to emerge. What once looked like random interference now appeared to evolve over time. Small variations in frequency were no longer isolated events. They formed sequences. Those sequences repeated, not perfectly, but closely enough to suggest consistency. It wasn't like a machine transmitting clean digital code. It was more like something natural behaving in a way that almost resembled structure. That distinction matters. Because in deep space, natural phenomena can sometimes imitate patterns. Plasma waves can resonate. Magnetic fields can oscillate. Charged particles can interact in ways that create repeating signals. But the precision required for consistent intervals is extremely rare without a stable source. And yet, the intervals were there. One of the most puzzling aspects was how certain pulses appeared to align with Voyager 2's own communication timing. The spacecraft transmits data in cycles, carefully timed to manage its limited power and maintain a stable link with Earth. Some of the anomalies seemed to appear within those same cycles. Not before. Not after. But during. That raised a difficult question for researchers. Was the spacecraft influencing the signal environment around it? Or was the environment somehow affecting the spacecraft's transmissions in return? The answer isn't simple. At these distances, even the smallest interaction can have unexpected effects. The interstellar medium isn't empty. It's filled with extremely low-density plasma, magnetic fields, and high-energy particles. Under the right conditions, signals can scatter, reflect, or even interfere with local electromagnetic behavior. But even with those factors considered, the level of alignment still felt unusual. Then came another layer of complexity. When scientists examined the Doppler data, the slight shifts in frequency caused by motion, they noticed irregularities that didn't fully match Voyager 2's known trajectory. But some of these shifts suggested additional influences. Not strong enough to indicate anything dramatic, but noticeable enough to stand out during precise measurements. There are explanations for this too. Interstellar turbulence can distort signals. Variations in plasma density can affect how radio waves travel. Even the rotation of Earth and movement of ground antennas can introduce small changes that must be carefully filtered out. Still, when combined with the structured patterns, the Doppler irregularities added another layer to the mystery. Individually, each anomaly could be explained. Together, they became harder to dismiss. The engineering team approached the situation the same way they always do, with caution, verification, and repeated testing. No assumptions. No leaps to conclusions. Every possibility had to be examined. Instrument error was considered. Voyager 2's systems are decades old. Components degrade. Sensors drift. Data corruption can occur. It's entirely possible for aging hardware to produce unusual readings that mimic meaningful patterns. Software interpretation was also reviewed. Modern analysis tools are far more advanced than anything available when Voyager 2 was launched. Algorithms designed to detect patterns can sometimes find structure where none actually exists, especially in noisy data. Human perception plays a role too. The brain is naturally wired to recognize patterns, even in randomness. This is known as pattern recognition bias. When dealing with faint signals from deep space, that bias becomes a serious factor. So the team did what scientists always do. They tested everything again. They compared independent datasets. They used different analysis methods. They removed layers of processing to examine the raw signal. They even simulated known space conditions to see if similar patterns could be reproduced artificially. Some results matched expectations. Others did not. The truth is, deep space is still largely uncharted territory. Not just physically, but scientifically. The farther Voyager 2 travels, the less direct comparison data we have. Every measurement becomes part of a dataset that has never existed before. That means uncertainty is unavoidable. But uncertainty doesn't mean something extraordinary is happening. It means we are still learning. For now, the transmission remains an open question. Not a confirmed discovery. Not a solved mystery. Just a signal that doesn't fully align with current models. And that alone is enough to keep scientists watching closely. Because history has shown that the biggest breakthroughs often begin as small anomalies, tiny inconsistencies that refuse to disappear no matter how many times they're tested. Voyager 2 continues to send its faint signals across billions of miles, each one taking hours to reach Earth, each one carrying a piece of a puzzle that is still being assembled. Somewhere in that data may be answers. Or perhaps entirely new questions. For now, all we can do is listen.